So thank you very much for giving me the opportunity to talk here. So I come from a very, so to say, different community. So I already apologize if few things I'm saying are trivial and a few other things are just a bit obscure. But what we were interested in is to study some particular flows of measures in the space of probability measure with square integrable moments. So here the fact that I put RD is just to simplify, but you should really think that we are looking at flows of measures on manifolds. And here I just put some very well-known ones, so the displacement interpolation of optimal transport, the Schrödinger bridge or entropic interpolation, and the Madelung fluid. So I will focus my talk on the Schrödinger bridge or entropic interpolation, which is nothing but the interpolation that you get by considering this regularized form of optimal transport. So the questions that we were interested in, since all these curves can be seen as some critical curves for some optimization problem, what are the Euler-Lagrange equations for these curves? So the answer is well known, of course, for the displacement interpolation. It's seen as a kind of geodesics in this Wasserstein manifold. For the Madelung fluid, this is also well known, or at least it's known. And we have seen yesterday a talk where we saw that the Madelung fluid is essentially the Newton, some kind of Newton's law. But for the entropic interpolation, this was not known, and this is the content it's part of the content of the paper. So the strategy is pretty clear. We have to somehow start off from an optimization problem, which is in a form which is it's not written in Wasserstein language, and we have to manipulate it until we get to a formulation where we can guess what's the Euler-Lagrange equation. So just a refresher, but here I can be very quick. This is the fluidodynamical formulation of optimal transport due to Benhamou and Brenier. This is the optimal solution is the displacement interpolation, which is seen as a geodesic, and the geodesic PD equation is exactly the fact that the derivative of the velocity field plus 1/2 the gradient of the norm of the velocity field square equals to 0. So now I want to introduce you to the Schrödinger problem, which is basically it's a problem on the space of probability on the path space, but once we project it on the marginals, it becomes exactly, for good choices, the regularized optimal transport. So here I consider the relative entropy on path space, this curly H, and the Schrödinger problem is to minimize the relative entropy against a prior distribution, which is P, which somehow represents the motion of a particle system at equilibrium under marginal constraints. So I assume that I start in u0 and I end in u1. So the Schrödinger bridge is the optimal solution to this problem. But as I said, this problem is posed as a problem on the probability measured on path spaces. So this optimal solution is much more than a curve, than a flow of measure, because it also entails correlations between different times. So to actually obtain an object which is tractable in the framework of the Wasserstein space, we have to consider the marginal flow, and this is called the entropic interpolation. So if you want to recover the regularized optimal transport, you should choose as P what we call in probability a stationary Ornstein-Uhlenbeck process, because it would give you exactly in the relative entropy, you would get out a square factor, which is due to a Gaussian, and will give you the Wasserstein. And we call the optimal value of this problem the entropic transportation cost. It's quite natural. All right? OK, now I just want to tell you the story of this problem, because it's kind of easy, and it's also kind of nice. It's in a paper by Schrödinger, which is quite old. And he said, assume that you observe a bunch of particles which are diffusing and are in thermodynamical equilibrium. And at time 0, they are more or less uniformly distributed on the space. Then you let them evolve for a unit of time. And of course, since you have many particles, you expect lots of mixing going on. So you expect their configuration to be, again, very close to the uniform distribution at time 1. But you assume that this did not happen. And Schrödinger question was, what is the most likely evolution of the particle system towards this unexpected configuration? So if you use large deviations, then you get exactly the formulation that I showed you before via the Sanov theorem. So so Schrödinger had in mind he had some plan about this experiment in quantum mechanics. So this plan is not dead today, but there are other reasons why you may be interested in looking at those Schrödinger bridges. First of all, as we have seen, they interpolate smoothly between probability measures. But at least for me, from my perspective, the most interesting thing is that they allow us to define what is the Brownian bridge between two measures. Because it's very easy to define the Brownian bridge between 2 points. But between two measures, you need a choice. You need to make a choice. You cannot just mix bridges at random. You have to choose a good mixing. The good mixing is given by the Schrödinger problem. But there are other things you can do here. I put something like, there is a tension in stochastic control, because you can reformulate the Schrödinger problem as a stochastic control problem. But probably this is not the focus here. OK, now I just want to refresh very quickly the construction of the Riemannian metric on the Wasserstein manifold, and what is the Levi-Civita connection, the covariant derivative, and so on. So of course, the points are nothing but the measures. And the tangent vector at a given measure is a gradient vector field, which is in L2. And the velocity of a curve is defined through the continuity equation. And the Riemannian metric on the tangent space is just defined by using the L2 product. So the good thing is that this Riemannian metric generates, as a geodesic distance, the Wasserstein distance. And this is exactly just one way of rearranging the Benhamou-Pranier formula. So it's the good metric to work with the Wasserstein distance. And the next step, which is somehow I would say a good success of optimal transport, is that you can explicitly define the covariant derivative of a vector field along a curve. Of course, if you ignore all regularity issues, which I am here, but you can even handle those. So the key notion to do that is the notion of flow maps. So we have the velocity field of our curve, and we just take the integral curves of the velocity field. They define the flow maps. And now if you have a curve in the Wasserstein space and a vector field along the curve, that means that for any time I have a vector field on the manifold, then we construct the covariant derivative at a given instant t equal to 0 in 2 steps. We first pick the tangent vector and compose it with the flow maps, and then project it down onto the space of gradient. So we first, basically, the flow maps take a tangent vector in mu t0 and brings in mu t and brings it back at mu t0. But since it's not going to be a gradient, we have to project it down on the space of gradient. This is not really the parallel transport, but it's almost. And actually, the final thing, now you have moved everything on the right space. You just differentiate there, and you get the covariant derivative of a vector field along a curve. And this will give you back the fact that the acceleration of a curve, so the covariant field of the velocity along the curve, is exactly this form that we have, this expression that encodes the geodesic equation. Indeed, the geodesic equation is just that the acceleration is 0. OK, so just here some list of functionals that we like. I mean, this is an energy functional, so just integrate the potential, the Shannon entropy, the Fisher information, and the key relation that I will use is that in this metric, the Fisher information is the norm squared of the gradient of the Shannon entropy in the tangent space. OK. So now let me give you the fluidodynamic formulation of the Schrödinger problem, which will give us the equation. So we choose as a prior law, so the equilibrium motion of the particles, the stationary law of a diffusion process, so B is a Brownian motion, and the vector field B may not be of gradient type, so we can even look at priors which are irreversible. And again, I recall you the Schrödinger problem. So the optimal measure Q hat, it is known that it is again a Markov process. This is a remarkable result, and you really have to prove it. But you can prove that the optimal measure is Markov. So since it's Markov and absolutely continuous, it must have a representation of this kind, where instead of B, you pick another vector field, which is CT. So the Schrödinger bridge is just a change of drift from the prior law. And for this, if you have two diffusions, which are mutually absolutely continuous, you have a nice expression for the relative entropy on path space, which is just integrating in time the mean square difference between the drift fields. You can easily get this via Girzano theorem and some martingale arguments. So this is good, but not quite good. No, so it's not over, because this CT has no meaning, no direct meaning from the optimal transport viewpoint. It's really clear what it means if you look at the diffusion. But to get a good fluidodynamic formulation, we should rewrite this CT in terms of the velocity field of the curve and of something else. But this is easy because you have the Fokker-Planck, and the Fokker-Planck tells you that the drift field is essentially the velocity field plus sigma over 2, the gradient of the log of mu t. And then finally, this is the fluidodynamic formulation that you get. Okay, so it's not just this, of course, there's more behind. But you see that you get exactly the Benamou-Brenier functional here, which you correct with the gradient of with minus the gradient of the Shannon entropy. And here you have this curly B, which is the projection on the tangent space of the vector field B. Because recall that B might not be a gradient, so you have to project it down to get something meaningful. But the result is that the optimal curve for this problem, which is now completely translated in the optimal transport language, is our entropic interpolation. And of course, now you can just do calculus, the usual calculus of variations, and you guess what the equation should be. Ah, no, this doesn't work. And there are no bad surprises. So the equation that governs the flow of the Schrödinger bridge, or the entropic interpolation if you wish, is exactly that the acceleration equals the gradient of free terms, which is, here we have the Fisher information. Here we have the norm square of the vector field curly B, and here we have an energy term, okay? Plus a viscous term, which accounts for the fact that you may have an irreversible prior, okay? So let me just comment a bit on these free terms. So you see that if you take a Brownian motion with very low variance, so you let sigma go to 0, this guy will vanish. And this exactly explains the fact that the entropic interpolation goes down to the displacement interpolation when you have a low variance. And these two terms here, they are they're kind of interesting for at least for probabilists. Probably probably here you don't fancy them so much. But in probability, so somehow there's been around for a while the question, if I give you a bridge, which kind of second order equation does this bridge satisfy? Because of the usual way we look at bridges is we just look them as other first order diffusions through this H transform method. And there have been different attempts to answer these questions. Actually, there are many somehow possible answers. But this, at least in our opinion, it's a pretty clear one. So it's really a second-order equation. The only thing which does not completely kill the question is that we still look at the marginal flow. And we cannot say much, actually we cannot say anything about the correlation between different times. But since we always, so there is always this interplay between stochastic bridges, Brownian bridges, and geodesics. So since we always think that a Brownian bridge should somehow be a kind of geodesic somewhere, so here is an equation that tells you exactly this, okay? And these two terms here, if you rearrange them in the right way, they express exactly some things which are called the reciprocal characteristics associated to a diffusion, which are again thought to express the mean acceleration of a diffusion. And the nice thing is that here you see that really clearly. So far, the best way to say that these things would express the mean acceleration was to do some short time asymptotics for very short bridges. And here, the nice thing is that you can go beyond the short time, so you can look outside the very asymptotic regime. Okay, I just want to give you a heuristic why this equation should be true. Actually, it's quite easy. So the slogan is that we have had so far is that particles start from a weird configuration, and they go to another weird configuration, but in the meanwhile, they have to minimize the entropy. So, I mean, if they did not have to end up in a weird configuration, they would start from the first bizarre one, and just go along gradient flow of the entropy, because they have to minimize the entropy, so the most efficient way would be to do a gradient flow. But of course, if you follow the gradient flow, you will just keep approaching the invariant distribution, so you will never reach the target measure mu1. So then you can do, you can be very cheap and say, okay, look, if I take a gradient flow, this is first order. But let's differentiate this equation once more in time at both sides. What do I get? And actually, you get exactly, in the case when the prior is just a Brownian motion, so there is no drift. If you differentiate this in time again, okay, here you get the covariant derivative of the velocity field. And here you would get the second derivative of the Shannon entropy applied to the derivative of the Shannon entropy. But this, because of the relation that I showed you before, is nothing but the gradient of the Fisher information. And now, if you consider this equation, you can even add one more boundary condition. And this is exactly the equation that the entropic interpolation satisfies in the very end. OK, so let me just finish by saying so what we can do with this and why it is interesting. So actually, this is the real reason why myself started to approach this problem. So you have this very basic question. So you have a particle system that starts in a given configuration and in another configuration. And you take a picture at time 1/2, and you want to know how does the particle system look like. So are the particles arranged according almost to the invariant measure? Or are the particles still very different, arranged in a very different fashion from the invariant measure? So in probability, of course, these questions, we ask it all the time. When we start from a probability measure, the first question that we ask is how fast a Markov process converges to equilibrium. This is exactly the same question, but here we have information at 2 different times, and we just want to know if in between the ergodic properties of the process were good enough so that the particles would look like the invariant measure. So of course, in classical optimal transport, where there is no probability, this is exactly the convexity of the entropy along the displacement interpolation. And here is what we get. So we get that the relative entropy against the volume measure, which is this curly H. So OK, this is a pretty ugly bound, and it would take a while to explain. But the answer is particles are pretty much like the invariant measure, provided you have good ergodic properties. which means good curvature and good variance of your Brownian motion. And this bound says that the entropy at any time is bounded by some constants that depends from the initial entropy and the final entropy. And then here you have the gain. So this guy with the minus will always be negative. So you have a gain which depends by some kind of complicated expression that multiplies the entropic transportation cost. Okay? So this expression here exactly tells you, if you, okay, here I cannot do the plot, but exactly tells you that the particles will be very, very close to the invariant measure at any time, provided you have good ergodic properties. And just a comment, if now you let this guy go to infinity, you get exactly the exponential decay of the entropy along a semigroup, which is exactly the logarithmic Sobolev inequality, for those of you who like this kind of things. But there are other questions which are kind of natural that we can answer. So one can ask, how big is the entropic cost? So a very beautiful thing about the Wasserstein distance is that although it's very hard to compute, you can always bound it with the entropy. And this is the Talagrand inequality. So now we try to look how to bound this entropic cost. And actually it turns out that you can bound the entropic cost between any measure and the volume measure by, again, some constant, which gets better and better with the ergodic properties of your reference dynamics, times the relative entropy of mu. And this is very, so if you now let sigma go to 0, you will see that this inequality becomes exactly the Talagrand transportation entropy inequality. But here it's really an entropy-entropy inequality. And the nice thing is that you dominate an entropy on path space with an entropy on the marginal lows. So you revert what you usually know, that when you marginalize, the entropy gets smaller. And in the same fashion as this guy here becomes Talagrand, this estimate here becomes, when sigma goes to 0, it becomes exactly the convexity of the entropy along displacement interpolations. There are other questions that we can address with the equation. So we know that as the sigma goes to 0, the displacement and entropic will become the same thing. But if sigma is not 0 and not small, you can ask how far are these two curves? And with the equation, you can have a hint of what the answer should be. And then you can also look at the question, is the Fisher information going to evolve in a convex way along these interpolations? And here I didn't put the answer, but the answer is yes, provided the interpolant is a log concave curve. And of course, if you have information about the evolution of the Fisher information along the curve, you can tell a lot about the shape of the measure. And finally, to conclude my talk, I just want to make a remark about the Madelung fluid. So I'm really not the person who can say a lot about physics, but we have seen this PDE system yesterday as well. This is the Madelung fluid, which is, so if you do some change of coordinates, you derive it with doing some change of coordinates from the Schrodinger's equation. And as we have seen yesterday, and then as it has been proven some years ago, you can have an equation for the mu, which is exactly the equation that you have for the entropic interpolation, but for the sign. So if you take acceleration equals the gradient of the Fisher information, you get the Schrodinger bridge. If you take a minus, you get the Madelung fluid. So I have no idea why this is true, and I have no explanation. But somehow it is curious that these two things, I mean, the Schrodinger bridges are somehow came out of an attempt to study quantum mechanics. This thing clearly as well. And you get two curves whose acceleration field is the same, but with a different sign. So the nice thing is that both curves are Newton's law on the space on the Wasserstein manifold, but with a different sign. Okay, I think this is really all. Thank you very much.
Thank you. So there is time for questions. Okay, I just have a question. So, so the entropy inequality
Yes.
is not working for in the case of the torus, then, for instance, the flat torus.
So yes, it's
And so-
not. So it's the same thing as for the Talagrand. So
Yes,
you need Ricci bounds. I don't for the flat torus. You don't, right?
And so can you just explain why the Talagrand inequality doesn't work in this flat torus case? Just
So the intuition.
yeah, the intuition. Yeah.
So okay, so there are many ways. So so the way I would tell it, but I'm not sure it's the one, is that if you are in a torus, there is no way to couple Brownian motions in such a way that they would converge exponentially quick. Because somehow if they because of this flat thing, how should I say? Because of the flat circles around the torus, you can never have a successful coupling of two Brownian motions which converge exponentially fast. So this is what, as a probabilist, I would tell you. I'm sure that this is not probably the, so to say, the most, probably it's not the first explanation that somebody would give you, but as a probabilist, probably it's the...
And so what happens on the sphere? Yeah.
On the sphere, everything works fine. The nice thing is that on the sphere, for instance, on the sphere, all these beautiful results about optimal transport, you can view them as the fact that you can start two Brownian motion from two different points on the sphere and couple them in such a way that they come together exponentially fast. And on the sphere, you can do that because you indeed have the Ricci bound. And since the Brownian motion somehow at any time looks at any direction, you just need an average version of the curvature, which is Ricci. And that's the explanation that I can give. And as for Talagrand, from this inequality, you can extract concentration of measure and some weird, which I still don't fully understand, sort of relaxation properties of semi-groups, which are at the moment a bit bizarre, but it's quite interesting. Okay.
So we have time for more questions. Okay, well, if not, thanks the speaker again.